Okay, so tonight we're going to talk about fancy processors just as soon as we finish dealing with interrupts here. So as I mentioned last time, interrupts are first of all like a subroutine call. So it's basically interrupts look like a subroutine call plus a mispredicted branch. And so what does that mean? Again, we said that it's like a subroutine call in the sense that all of a sudden you're in the program flow and you go off to somewhere else. And then when you finish executing the interrupt routine, which is, something like read the character that you just poked at on your phone. And then after you read that character in and, put it into the message, then go back to whatever you were doing before. And so it's like a subroutine call in that sense. You go off to somewhere and then you come back. And we just noted that we have to have a special register for where to come back to, because we can't trash the RA register, because you might already be in the middle of a subroutine call, and so you can't trash that register. And then the second half, so that's one, and then two, the second half, it's like a mispredicted branch in the sense that when you do go off and take an interrupt or an exception, you kill off, you make no ops out of everything else that's in the pipeline. So the instructions that are after the instruction that you interrupt, they get killed off. So you turn them into no ops, and you do that so that the operating system knows exactly what instruction it is that is the last one that completed, so that it knows when it comes back, it can just start up and continue on from there. So that's all we'll say about interrupts. Again, what they're useful for, of course, is for doing things that happen asynchronous to whatever video processing or whatever it is you might be running. Again, like a message comes in or whatever. And the so that's what we use them for. And the hardware that it takes to handle them, again, looks like a combination of this subroutine call and mispredicted branch. So if you look at the hardware that they add, which we're not going to look at in detail, you'll see that's what it looks like. We'll get there in a second. So here it is. And you see that, let's just take an example. So we see all the stuff that was in our picture before, and all that stuff hasn't changed. This is all the same. So you see the first thing that happened here is all of a sudden in this mux control here, we have now an OR gate. So now we've seen an AND gate in our pipeline and an OR gate. So this OR gate just says, okay, I can bring these muxes, I can bring this 0 into all these places, either because it's a mispredicted branch, or it's a hazard, right? We killed an instruction when we had a hazard, and now we have the case of we're gonna kill it when we take an exception or an interrupt. So that's what the OR gate does. It allows us to use this mux and put this 0 into these locations in 2 different ways. That's what the OR gate does. It says do it if this is true, or do it if this other thing is true. So that's what we're doing. And then you see downstream we can put zeros in here as well. And so it allows us to kill more than one instruction. It allows us to kill put multiple no-ops, kill instructions at multiple stages of where they are, not just starting from the A stage and going forward, but you can also do it from the memory stage going forward. So anyway, so the thing to take away again, interrupts, exceptions are like interrupts. Interrupts are handled the combination of a subroutine like call and a mispredicted branch. Again, we have to put the PC in a special register. We can't put it in the RA, not RA, which is what we use for a normal subroutine, because RA has to still be valid if we come back and continue to execute. So we can't use RA. So we have to use the special register, the exception program counter. Oh, we don't care about this example. We don't care about multiple exceptions. We don't care about imprecise exceptions. Oh, I'll make one comment about imprecise exceptions here. From a hardware perspective, very easy. Because you don't tell the operating system exactly where the exception happened. You tell it, oh, it happened somewhere around here. And so that's very easy for hardware designers to do. They really like to do it that way. And here's a case where the software people said, that's you people. Software said, yes, you can do that if you want. But we will never use your processor. And so the result of this is that there are no hardware, there are no microprocessors out there that implement imprecise exceptions, because if you do it, no one will use it. Software people will just reject it, and you'll never sell any of them. So I don't even know why the author talks about it. All right. This new TLA that we have here, ILP, which stands for instruction level parallelism, is extremely important. Instruction level parallelism says, hey, let's try to do more instructions in parallel, just kind of how it sounds. And one obvious way to do that is you can make the pipeline longer. Deeper is the same as longer. And we know that when we made it, 5 stages, we got a 5x improvement. So you would think, well, if we make it 10 stages, we'll get a 10x improvement. But the problem with that is that there isn't an obvious way to divide up the pipeline into 10 stages. For example, if I divide up the pipeline into 10 stages, I need to make the adder, since it defines the time to do one stage, we need to divide the adder in half, first half of the add and a second half of the add. And of course, since the add isn't done halfway through, you can't bypass from that point. So even though you're doing adds at a faster rate, you can't get to them because they're not really done. So deeper pipelines, don't work very well. And there was a classic arms race, and an arms race is a generic term for multiple people doing the same thing and fighting over who has the best. The classic arms race is the nuclear arms race between the United States and the Soviet Union. Anyway, there was an arms race here as well between Intel and everyone else. And I think we'll see it on a slide. Later on we'll see a processor that Intel did that had 20 plus pipe stages. And when they were finally done with it and introduced it into the market, it burned twice as much power as the previous processor. And you could guess that, because remember that power, we learned, is equal to the capacitance times the voltage squared times the frequency. So you can imagine if you say double the pipeline depth, that you're going to therefore double the frequency. That's kind of the whole point. So you see that the power therefore is going to roughly double if the frequency roughly doubles. And the problem is that the performance didn't improve. And so they came out with a processor that was, burned twice as much power and didn't perform any better than the previous generation. And that was the end of that arms race. And that started the multi-core processor arms race, which is one of the two arms races we're in now. We're in a two-dimensional arms race right now. One dimension is how many cores you can put on, and the other dimension is the how much ILP you can get using what we're going to see in a minute, which are called out of order processors. And we'll see in a minute what out of order processors means. So the first step of building an out of order processor is this idea of multiple issue. So instead of making the pipeline deeper, we make the processor wider. And we're going to look at that in a little bit of detail here. And when you start issuing more than one instruction at a time, and that's what this means, multiple issues. So you're trying to, on every clock cycle, you're going to try to say do 2 or more instructions. That's the idea. And so if you can manage to do more than one instruction per cycle, then the CPI, of course, becomes less than 1. So people start talking about the IPC instead of the cycles, instead of how many cycles per instruction, it's how many instructions per cycle. But they are merely exactly inverses of one another. And it turns out that in reality, CPI is much more useful, because you can add CPI, as we'll see later, and figure out, when we get to chapter 5, what the memory system latency does to our CPI. So we'll mainly continue to calculate in CPI, but we'll note that people are very proud if they can have a IPC that's greater than 1. So a typical state-of-the-art multi-issue processor these days is right here. This is what it looks like, which that's kind of sad, because we've looked at many other slides in this slide deck that we've said are out of date, whereas this slide is just as old as those. But if you look at a multi-issue processor today, this is, again, still what they pretty much look like. And why is that? Well, the reason for that is because there isn't really that much ILP available. Hardware people would like to imagine that there's an enormous amount of instruction level parallelism. And again, what does instruction level parallelism mean? It means if I look at a program, if I look at a small piece of a program or a big piece of a program, and I look at it all at the same time, just look down on it, how many instructions can I find that I could execute at the same time that aren't dependent on something I've done in that, in the thread of that execution. And we know, you and I know, just from looking at programs so far, the ones we've written and the ones we've looked at, is that usually when you compute something, you use it. And then after you compute that, you then use that. And then after you compute that, you then use that. That's how programs work in general. So that means all those instructions we just talked about are dependent on the previous instruction. And so that means that it's as simple as that. That means that you cannot execute those instructions at the same time. Each one is dependent on the previous one. And because that's the nature of the way programs are, you can therefore imagine that the amount of ILP is actually somewhat limited. And it is somewhat limited. And again, that's why in general, you don't see processors, much more complicated than trying to issue 4 instructions at a time. Because if you try to issue more than that, you'll just find that you have nothing to do. And even trying to issue 4 at a time, you don't get anywhere close to completing 4 at a time. It just doesn't even come close. But that's the goal of out of order processors, is to look through the instruction stream and find all the possible instructions that they can and try to execute them as quickly as they can. Now we talked about one problem with this, and one problem being that our just imagination of the way a program works is that you compute something and then you use that, and you then compute something else and you use that. And so so they're naturally dependent. Every instruction is dependent on the previous. That's just happens naturally. The other thing that happens is that we know that on average, that there's a branch every 4 instructions. Branches are 25% of the instruction mix. And so if you try to look at a big window of the program, you've got the problem that instructions are nominally dependent on one another. And then the other problem you've got is that, you don't know which way that a branch has gone or will go. And so to get any sort of decent ILP, you have to have absolutely magnificent branch prediction. Because if you don't have really magnificent branch prediction, you can see what happens with the mathematics. If your branch prediction is only 80% accurate, then after 2 branches, you're 0.8 squared. That'll be the likelihood that you made that right decision, and that's 0.64. So if your branch predictor is 0.8 accurate and you make 2 branch predictions in a row at 0.8, then the likelihood that you made that you're still going down the right path becomes 0.64. And after 3 branches, it's 0.8 cubed, of course, and so on. And so this function goes down really, really fast. And so, if your branch predictor is only 0.8, and if you look at a window, of out past 3 branches, you're only 50% likely to be on the right path. And so anything you do down that path, you're 50% likely to throw it away. And of course, this is the whole notion of what's called speculation. So when you're out executing instructions past the current branch, you're basically speculating, because you've made a guess as to which way the branch path is going to go. And so again, if you're 0.8 and you're 3 branches out, your speculative execution is only 50% likely to be useful. So that means that 50% of the stuff that you compute, you're just going to throw it away. And of course, that's very, very, that uses a lot of power and delivers no performance. And so you better have a branch predictor that's, more in the 0.95 prediction, rate than 0.8, or you just might as well forget, trying to extract a lot of ILP. So this is the second reason why people throw zillions of transistors at the branch predictor. Remember, the first reason was because when you're wrong, you have to throw away a bunch of instructions. The second reason here is that if you aren't very, very accurate, then if you try to look out and extract and find more instructions in order to extract more ILP, you need to be very, very high accuracy. Otherwise, the function of 0.95 to the n, where n is the number of branches that you've gone by, number of branches traversed, is that function will, goes down very fast if this number here isn't very, very close to 1. Obviously, if it's 1, you're in great shape, right? Because 1 squared is 1, and 1 cubed is 1, and 1 to the 4th is 1. Everything's great if your branch predictor is perfect. So you got to get it as near perfect as possible. Okay, so a lot about instruction level parallelism there. That's kind of the basis of many, many things we're going to talk about here going forward. So we're going to look at both these things. We're going to look at static multiple issue and dynamic multiple issue, because static multiple issue will lead us to why we want to use dynamic multiple issue, and we want to see the simple case first, and then we'll generalize to the more complicated case. Okay, so again, as we said, speculation. you guess what to do. It's that simple. That's what speculation means. It means guessing. And so we look past the branches, and we hope that we're right. Hopefully, made the right decision about whether we took the branch or not. And if we did make the right decision, great. Then we're done. We can save that result. And if not, we have to throw it away, and we got to go back and take the right path. So a lot of cost to going the wrong way. Huge cost to going the wrong way. You've got to throw away everything you did, and then you got to go back and redo it all. So there's the case. We won't talk as much about speculating on loads, but you can do that too. You can guess as to what the next thing you want to load is, but we don't need to complicate it with that. We can just concentrate on this guy here, and it'll give us all the flavor of what has to happen, everything we need to know. So again, in static, we're going to ask the compiler to order things for us, and in dynamic, we're going to have the hardware reorder things. It's that simple. Again, this was the static, and this is the dynamic. Two cases. Oh, we don't care about this. Too much detail. We want to see the beef. So here we're going to see this in a second, that when you do static multiple issue, that a lot of times you won't have anything that you can issue, and so you'll see a lot of no-ops get put in by the compiler, and so we'll see that in a second. Picture is worth 1,000 words here. So here it is. Here's our processor with static dual issue, and it looks pretty much exactly what you would expect. But here's what we do. We divide our, we have our 3 classes of instructions that we've talked about since the dawn of time. We have our ALU, our branch, and our load store. And so we take and we create 2 parallel pipelines as you can see right here, is 2 parallel pipelines. And down one of them, we can put ALUs and branches, one or the other. And down the other pipeline, we can put loads and stores. And so you see that we do that every time. We have pairs. We issue the instructions as a pair of instructions, a static pair that the compiler, creates for us. So it looks at the code and creates pairs of instructions. And just to be clear, we'll end up talking about processors that are called VLIW in a while, which stands for very long instruction word. VLIW, very long instruction word processors. So about 15 years ago, somewhere right around there, Intel decided to do a VLIW processor, mainly because they just wanted to distract the world and convince the rest of the world that they should go off and do VLIW processors. And Intel really only was spending a few percent of their income on this, and they were really spending all the rest of their money continuing to do the x86 instruction set and trying to get everybody else to go off and do this stupid thing. And they sort of succeeded, and they built their own, spent billions of dollars on it, and then finally just killed it once it completed its purpose, which was to just distract everybody else. So anyway, they built this VLIW, and a VLIW is exactly what it says. Instead of a 32-bit instruction, we'll have like a 128-bit or a 256-bit instruction. And the reason we bring that up now is because basically what we're asking the compiler to do here is to take our two of our 32-bit instructions and combine them together into one 64-bit instruction. So what we're really doing when we do this is we're making a medium, an MLIW, a medium long instruction word processor. That's basically what we're building. And it turns out that if you build a medium long instruction word processor where your bundle of instructions that you put together is 2, you can actually make it work pretty well. And in fact, almost every processor on the market today that touts itself as being relatively high performance does 2 instructions, issues 2 instructions per cycle. And then out on the lunatic fringe, again, they're doing 4. But if you want efficiency, if you do 2, you get a really good, efficient process. And again, so every time we issue 2 instructions, parallel instructions. And so you can imagine what the hardware looks like for that. It looks exactly like we'd expect it to. Look, parallel to each other, we have 2 ALUs. Just what you'd expect. Because down this path, we need the ALU, remember, to do the load store, because we can do a load store address calculation. And at the same time, we can be doing an add, a regular add or subtract. And so we need 2 ALUs to do that. We need one to do the add subtract and one to do the load store. And then remember also, we put branches down this pipeline also, so we can do branches here. And remember, a branch just requires this ALU to do a subtract, right? To see if the two operands are equal. So we can do branch on equal or branch on not equal. And so we've got everything we need here to do add subtracts, and of course to do the subtract for branches. And then we've got our ALU here, which really we don't need an ALU. Really, all it is an adder, because all it is doing is the is the base plus offset for our address calculation, our data structure base address plus where we want to go into the data structure, that same old computation that we've talked about forever. And then the program counterpart stays exactly the same. It's very simple because the only changes is that we're incrementing by 8 instead of by 4, because we're moving 2 instructions at a time. And so that part's very simple. And the other thing it's clear that we need is that we need twice as many read ports on the register file, because we got to feed 2 into here and 2 into here at the same time. So we have a register file with 4 read ports instead of 2 here and 2 here. And then of course we have to have multiple write ports. We have to be able to write the result of an add or subtract, and we have to be able to write the result of a load all at the same time. So many things are doubled, some things are not. So things that aren't doubled is the incrementing of the program counter. And since we can only put load store down one of the 2 paths, we only have 1 data memory still. So we don't replicate the data memory. So we don't replicate the instruction memory, we don't replicate the data memory. And those things are quite large. So we'll see in chapter 5 that if you had tried to replicate those, that wow, it would be very, very expensive. You really don't want to do that. So here's our picture. Looks again pretty much exactly like we'd expect. 2 ports feeding an ALU, 2 more ports feeding an ALU, multiple write ports coming from both our sources to do writes, and then a single way to increment the instruction. Pretty much exactly like you'd expect. And we'll see in a minute how it works. So here's the big problem that we're going to have immediately is that before, remember, we had a load to use of 1 cycle. So the load to use hazard, it says here it's still 1 cycle, but it's 2 instructions. So it says more aggressive scheduling required. So let's go off and just briefly make sure we understand what the problem is here, because this is a really important point. So here's our pipeline. And recall that we're gonna issue 2 instructions at the same time down each of these in parallel. So a top one and a bottom one, if you will. And so the problem is if you issue now, if you have a load followed by an add that uses the result of that load, normally the load would have been here. Whoops, the load would have been here and the add would have been here, right? And we had to put just 1 no-op down the pipe, remember, because here's the MIM stage. So here's when we get the result of the load and we're able to put it into the ALU stage here. So that's our 1 cycle stall that we have to put in for the load to use. Remember, load to use stall. So the problem here, right, is that now you could put the load here and the add here. And clearly that's not going to work because then the adds ALU cycle is here. And so this memory can't possibly feed this ALU. That can't happen. And so the ALU, and of course the ALU instruction, the add instruction, I mean, it can't be here either, because again, we can't feed it until here. So as we try to issue 2 instructions at a time, you see immediately that we run into a horrible problem of how many instructions there has to be between a load and an add. So you see that the number of cycles still had to just be this 1. You had to have this 1 extra one here. but the number of instructions now is more than one because we're issuing them in pairs. So if we have this first one as a load, it can't have the add here. And so the first place it can have the add is in the next instruction. So we could put this add here. But that is still going to move down. It still has to move down because it, it still can't happen in the next, in this load to use stall slot here. So that's the point that the author is trying to make in the previous slide. He says that it's still one cycle, but it's multiple instructions. Oops. Come on. Why are we here? That's not where we want to be. What happened? There, thank you. Okay, so again, can't use ALU result in load store in same packet. So that's clear. So split into 2 packets, which is basically putting in a stall, but you're still going to have to deal with this latency of the load to use. So you're going to have to put in the stall cycle anyway, even after you break it into 2 packets. So you can see that this is all going to cause a lot of performance advantage that you would hope to get from the dual issue to go away. And so he says here, very calmly that more aggressive scheduling is required. And so we're going to see what that means and how we might do it. Because if we don't do something, clearly this is not going to work out. And here's the example showing it not working out. So here's our loop that we want to execute. And we can see that because of the dependencies of the loop, that the best we can do is this piece of code here. This is the best we can do with our two pipelines. And so you see that because we've separated into load store and ALU branch, and because from the time to do this load until we can get the result is here, we can't put this instruction until down here. And we can't do this instruction until we have this instruction, right? And so the best we get is we get 5 instructions, count them, 1, 2, 3, 4, 5, only 5 instructions, and we get them done in 4 cycles. So our IPC is 1.25. And we would hope that after we, put in all that extra hardware into our processor, that we would have gotten something closer to 2. I mean, we doubled the register file ports. We doubled the number of adders that we had. We doubled the amount of bypassing that we had. A lot of stuff got doubled, as you saw in that picture. And yet our result was an IPC of 1.25. Very sad, very sad. Okay, so what can we do about that? So in the next lab, whenever we get to it, I think it's this loop unrolling lab. So we're gonna actually do this ourselves. But right now we're just gonna look at this piece of code we just did and see how it works. And so basically what we're gonna do is we're gonna quote unroll the loop, which means we're going to take that piece of code and we're going to replicate it some number of times. And we're going to replicate it 4 times, which is often a very, very reasonable number. And so let's just think about that philosophically for the moment. Remember that, we went to all the work to, define the mechanism to have a subroutine call. And we did that so that we could keep from, replicating, for example, the square root code, right? We said, oh, we don't want to have that square root code be in our program, every time we call it. We don't, it makes the program much larger and hard to read and all that stuff. Well, here all of a sudden, we're going to take a piece of code that would otherwise be only five instructions, and instead we're going to expand it out to be 20 instructions or slightly less, because we don't need to check the loop every time. So we're doing the opposite of what we said before. We're actually, we're making the program bigger. And this is because when you run a program, you analyze what it is where the program is spending its most time. And if you see that it's spending its most time at this one location or this one set of instructions, you want to optimize those instructions. And not having 20 copies of the square root routine in your program allows us to have the luxury of taking these other pieces of code, like this really important one here, and unrolling it so that we can get better performance. And the important thing is, when we unroll it, is to use different registers every time you replicate the code. And this has a name, and it's an easy name to remember. It's called register renaming. So you're renaming the registers that are used, on a per iteration of the loop. And then they have this fancy word here that basically just means, false. Much easier if you call it false dependencies. So dependencies that aren't really there. So if you don't use different registers for the different replications of the loop, then when the compiler looks at the code, if it doesn't use different registers, it can't move the instructions around, because it looks like all the instructions are dependent on one another, even though they're really not, right? Because they're a separate iteration of the loop. And since they're a separate iteration of the loop, that they're not, working on the same thing, right? Because one loop was done and then the next one is done, right? So we want to rename those registers so that we can then reorder the code, and that's what we're going to do. So we're gonna not do this, avoid loop carried anti-dependency. That's really hard to understand. Again, all it means is that we want to make sure we use different registers so that we can then move the instructions around without them looking like they depend on one another. Okay. And this register renaming concept that we're gonna look at here and see how it helps us is the same thing that the hardware does dynamically when we look at the dynamic scheduling. Again, here we're talking about static scheduled machine, right? Where we just create these packets. But now we've unrolled the code, and having unrolled the code, the compiler is going to be able to create much more efficient packets, which we're about to see. And the hardware folks said, oh, okay, we get that, we understand that. We can actually do that in hardware. And again, that's what out of order processors do. They use register renaming so that they can reorder instructions that really aren't dependent on one another. Okay. So here's the unrolled code. And if you look at this code, all it's doing is it goes, here's the path, right? Here's the path. It goes here, here, and then here. And it goes here, here, and here, right? It just keeps doing, it does this thing over and over. But instead of writing it, linearly, we're now able to put this add at the same time as this load, because by using different registers, none of these things look like they're dependent on one another. So we took T0 and made it into T0, T1, T2, and T3. Okay. So we just changed the name. For every load word, we used a different register for its destination. And having done that, we can put these four guys right next to one another and overlap them with the loads as they're happening. And then as soon as we're done with the loads, we can start putting in the stores, because we can put this store in as soon as we're done with this, with the thing that computes the result for that store. So you can look at this piece of code and you can see that renaming the registers and replicating the code 4 times, that we now get this. We get done in 8 instructions, count them 1 through 8 here. He's counted them for us. We get done in 8. What would have taken 14. And so we get 1.75. And he says at the cost of registers and code size, well, that's what the registers are for. That's why we have them, so that we can do this. So that's not a negative, that's a positive. That's why we have 32 registers, so we can do this. And he says, and the code size goes up. Yeah, clearly the code size goes up. But again, the whole point is that the reason we have subroutine calls and try to keep all the other code as small as possible is so that when we come to the thing that is determining the performance, right? We've analyzed the code and we see that our code was spending 90% of its time in this loop. And as soon as you see that, you say, oh, okay, well, I'll unroll that loop. And when I unroll that loop, I can have it so that the program is now only spending, instead of 90%, 90% divided by, 1.75. I can make it way perform way faster by doing this. So again, so you're going to take your inner loop of the multiply and just unroll it, completely, and first just unroll it once, and see what happens, in terms of this, just you'll see how easy or how hard it is to do that. Okay, so dynamic multiple issue again. So the new news here is, as we just said, that dynamic multiple issue just does what we just did by hand. It just does it on the fly. So it does register renaming on the fly. And this takes an enormous amount of hardware. It's simple to think about, simple conceptually, but getting it right is really, really difficult. It's an enormous amount of hardware and very timing. Very timing critical. So it becomes very, very difficult to keep your cycle time of your processor at a very high rate when you do this. So you spend an enormous amount of power making register renaming keep up with the speed of our adder. Very, very difficult to do this. And so, billions have been spent. Intel, has done 20 generations of processors with register renaming now, and each one is a little bit faster than the previous one, and a lot more power. So here's what we do. Again, allow the CPU to execute instructions out of order. So here's this term. And this term has become so important that it has its own, little TLA here, OOO, out of order. So all modern, very high performance processors are all out of order processors, which means they issue the instructions in whatever order they want. You know, they just go out. And again, remember what you're doing is you're looking for ILP. You're looking for instruction level parallelism. You're looking for something to do that isn't dependent on something else. Because if it's dependent on something else, you can't do it. So you're looking through the code, looking for things to do. And not only are you looking through the code, looking for things to do, you're looking down a particular path of the code because you don't know which path you're going to take, you know, through branches. And of course, you can handle that multiple ways. You can assume your branch predictor is perfect and go as deep as possible. Or you can assume your branch predictor isn't really perfect and you can go wide. You can just go multiple ways down a path, which means you know, so there's terms for this, right? There's depth first. And there's breadth first. So depth and breadth. So depth means, you know, follow, you know, you assume your branch predictor is correct and keep going down the way it tells you to go. And you can, you know, look out. Today, modern state-of-the-art processors, they do that, you know, for a window that's 128 instructions. They'll keep looking. And that's the way that's typically done. Breadth first, you could do that also. You could just assume that your branch predictor isn't that great. And you could go in multiple directions, you know, take all the possible ways to the branch. The problem with that, of course, is that you know that you're going to throw away, you know, the deeper you go, you know, you're every time you take another step, you know that you're going to throw one of the paths away. So very quickly, you're in the situation where you're computing the right result, you know it because you're doing all of them, but you know you're going to throw away almost all of what you've done. You're going to keep one path out of, you know, when you're three levels deep into this thing, one of the things is right, and you know that 7 of them are wrong. If you go one more level deep, you know that one of the paths is right and 15 of them are wrong. So you can imagine how much power you're burning to try to get some amount of depth into that tree. So anyway, so nobody does this and everybody does this. And they spend all their transistors, a ton, gazillions of transistors, making their branch predictor as absolutely as good as possible. So, you know, his example of code here is he says, you know, okay, if you look at this code, just look at it, you know, this subtraction instruction here isn't dependent on this guy. And the add is, of course. And so all he's saying is that, okay, I can execute this instruction before this one, right? I can do them out of order. And in fact, you know, once he does this one, then he can do this one, but these two are dependent, right? So this code here isn't ridiculous. He hasn't come up with some incredibly ridiculous, you know, case because he's got, you know, he's got these two are dependent and these two are dependent. The only thing that's not dependent is that this one doesn't happen to be dependent on this one. And you know, and that will happen. This is a very reasonable, you know, looking snippet of code. You can see this all the time. So there is one instruction that you can go off and start to try to execute while you can't do this one because of the load to use stall. So basically you're reordering these dynamically. You're issuing the instructions out of order, right? This one in program order is after this one. But in execution order, you're going to put this one up here dynamically. Again, the compiler again could have done this for you, but you're doing it dynamically. So that's what hardware designers like, to develop really fancy processors that the compiler could have done. It's all about where the money goes. Okay, so here's what a CPU looks like that's out of order, dynamically scheduled. It starts to not look quite as much of a pipeline, although the pipeline is still here. It's now being drawn in this dimension, but the pipeline is while it's there, you've got all these other things that are happening because of the reordering and because of the out of order. So, that's the same thing. So since it's since it's out of order, right? You've got these reservation stations where you are waiting for the stuff to get done so that you can put it into the load store or into the adder or whatever. And then finally, when you're all done, you have to complete the instructions in order. So that's really the other important thing on this slide, is that you have to complete the instructions in order. And you have to do that because remember about precise exceptions. Because when you take an exception or an interrupt, you have to make sure that all the instructions before the instruction that takes the interrupt are done, and all the ones after it, none of them are done. And so in order to do that, you're going to have to commit the instructions in order. So out of order issue and in order commit. Those are the two things: out of order execution or issue, in order commit, in order get done, so that you can maintain. If something goes wrong, you can tell the software guy exactly what was wrong. Okay, we talked about register renaming. It is exactly this. This is just a bunch of words, but we have the idea in our head. Just think about that static code. What did we do in that static code so that we could change when we unrolled the loop? We wanted to then move the instructions around so that we're not continuing to do it in the same exact order. We want to mash it all up because we've got a dual issue processor. And in order to do that, we had to rename the registers. So if you just think about that and look at that model, you can see then exactly what's happening dynamically. And it's conceptually no harder dynamically than what you did when you statically did it. It's just that you're doing it on the fly dynamically, which is just really hard to do from a implementation, verification, and timing perspective. But conceptually, if you just understand that unrolling case, you understand the whole thing. We already talked about this. We don't need to say this again. We're going to ignore this because it's the same thing. It's just in loads instead of doing branches. But again, we predict branches and then we continue issuing. And of course, again, you can't commit any of these instructions until you know what happened with the branch. Till which way did you really go down that path or not? So because you have to be able to back up if you did it wrong. So you can't write the register file with the real result until you know whether you did the right thing with your branch prediction. So first you predict, then you do whatever you hope is the right thing. And then once you find out whether you did the right thing or not, then you can either go back and redo it, or you can say, yeah, I'm done, and commit the result and continue on. And so here he says, well, okay, why we don't just let the compiler do it all. And there's a bunch of reasons. And really it mainly has to do with branches and cache misses. And we'll talk about this is what chapter 5 is all about, and we'll see how bad cache misses, what a problem are. But we already know the problem with branches, right? That the compiler sadly does not know which way the branches are going to go. At compile time, you do not know. So inherently, a program is dynamic. And so since inherently a program is dynamic, that's why in the end, you have to do dynamic scheduling, dynamic register renaming if you want to get the best performance. Because programs, sadly, because of branches, are dynamic beasts. They don't keep doing the same thing over and over. The branches are unpredictable, and the hardware tries as hard as it can to predict them, but the compiler cannot. The hardware is able to do a very good job predicting them because once it's running the program, it keeps a history of what they've been doing. The compiler can't do that. Now, there are issues of compilers that if you're running a program enough times, that in the past they talked about having a compiler, run the program a bunch of times and figure out what the patterns are of the branches, and then use that to do static scheduling. But that's not the way the world went. The world went, to doing it all in hardware and letting the compiler writers go off into do something else. So anyway, so does multiple issue work? Yes, but not nearly as much as we'd like, or as much or as well as you would expect for the money spent on it. Billions of dollars spent to get 2,3x performance versus Moore's law, which has given us, from 1 megahertz to 4 gigahertz, right, over that same period of time. And that's a fair bit more than 2 to 3x. And we're talking 1,000x. So, if you have a choice of where to spend money, do you spend it on technology or spend it on multiple issue? I can tell you where you should invest. Don't invest in multiple issue. Here's the understatement of the century. Well, if you guess right, then things will turn out well. That's what this sentence says. When you guess right, it'll turn out well. The better you guess, the better you'll do. You can say that about everything in life. The better you guess about the future, the better you can be prepared for it. Okay, so here is that processor that I mentioned earlier. 22 pipeline stages. Oh, actually, this is the one that was semi-successful. Here's the one that fell off the cliff. 31 pipeline stages, 100 watts. And then again, very, very quickly replaced by the original Core Duo was the first thing out, right? They started calling the processors cores. And the first one out was this Core Duo. It had, two processors that went all the way back, right, to approximately here. They were 14-stage processors, instead of this guy here, which was 31, which was a huge failure in the market. And so they started bringing the power back down by doing that, of course. And then these aren't even Intel processors, so can't really even compare them. But you can see what Intel did, up, 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 and then finally down. And today, of course, we're going, heavily down this path. And many people are doing it, more aggressively than Intel. Intel, has a lot of momentum behind building the highest performing single thread processor that you can, and there's a certain class of customers that demand that. But there's other classes of customers like the data center folks, where they're basically processing requests from thousands of users, where that problem is to use the term, remember, that we used before, embarrassingly parallel the problem of, servicing, millions of users searching the web is an embarrassingly parallel problem. You can throw thousands of processors at it because they're all doing something different. All those things don't have to cooperate together. And again, the whole point of this slide, of course, is that all that speculation requires a lot of power. It just requires a lot of power to do register renaming and keep up with the cycle time, and it requires a lot of power for all the things that you throw away. Everything that you throw away is power completely wasted. Every time you made a misprediction of some sort, you wasted that power. So I don't know why they're comparing these two particular processors, other than just to show that they're completely different classes of processors. When you run programs on these two processors, you will get wildly different run times. We don't care. So here's a slide that it's worthwhile just to spend just a couple minutes on, just because not that one, this one, just because when we get to chapter 5, we're gonna talk about cache misses, and we don't really know exactly what that means yet, although we can imagine that there's, the cat photo is out there on disk somewhere, and we want to look at the cat photo, and we have to bring it into our processor, and that takes time, and that's going to cause us to miss in our cache. When we tried to load that whisker, it wasn't there. We're going to have to go out and get it. And so here on this axis is CPI. And these are all the benchmark names of the spec benchmark suite that we've talked about in the past. Spec benchmark suite. And let's see, the really one of the really interesting programs in here is GCC. That's the GNU C compiler. And you see that program, for example, has a ideal CPI down here, right? That's its ideal CPI on this A8. And then here's how much time it spends on pipeline stalls, which means load to use stall and branch mispredicts. So you see it throws away a huge amount of performance on this stuff. And then finally, it's got a bunch of memory hierarchy stalls, which means cache misses. But we'll see when we look at the Intel processor that again the A8 is a particularly not great design, right? I'm not even sure it has a branch predictor in it, which is why it's throwing so much away on branch mispredicts. But it's you always look at a processor in this regard. You always look and say, okay, well here's what I could do, best case, and then here's how much I'm throwing away on this kind of stuff, and here's how much I'm throwing away on this cache miss kind of stuff. And this is how you design a processor. And you look at what you've done and you say, well, this didn't turn out very well, and so I need to fix this. And of course, the Intel folks were off trying to design something completely different, and they do get a much better result. So their processor is fast enough that they're spending way more time in cache misses than in other stuff. So their ideal CPI is down here. And you, unfortunately, you have to put these, it's hard to put these slides together to figure out exactly what's going on, but you'll just have to, we'll just have to imagine that these light blue things here have more cache miss time and less branch miss predict time. And sadly, they don't really allow us to see that very clearly. They probably didn't want us to know. All right, let's see. We don't care about Intel's matrix multiply. We do care about this. All right, so AVX, I don't know if you mentioned this or not, but AVX is just the, is the marketing term for SIMD. So that's Intel's name for their SIMD. And again, remember, SIMD means, doing like 4 multiplies in parallel. When you have something like matrix multiply and you've got all these multiplies to do that are not dependent, you can do them all in parallel. And so it says, okay, if I take a piece of code, that matrix multiply, just like the one we have, and I just run it on without SIMD, I get this performance. If I use SIMD, because I know I've just got a whole bunch of multiply adds that aren't dependent, so I can do them all together, I get this. And then if I unroll it and get rid of the loop overhead and get more multiple issue going on, I can do even better. And so this is our goal with our whole matrix multiply routine, and is to see that this is what happens, or what we can do. And again, we just want to realize that the matrix multiply is, why is it important? Again, it's fundamental to AI ML, to all the current AI ML algorithms. It's, all the games out there are nothing but doing, matrix multiplies.
Doesn't that happen on the GPU though?
Yes, absolutely. Yeah. Yes. The GPU is doing those matrix multiply because they're all in parallel. And Intel now has a new, GPU that they've just introduced, trying to compete, directly with NVIDIA in that market. But what happens, is still, what happens in the GPU is basically this, right? It's the equivalent of doing it, gazillions of them in parallel, right? So it's like taking the CPU that we're thinking of here, where this is unoptimized, and then we use SIMD because they're all those things are SIMD, and then unroll it so there's no branch overhead, and you can keep the thing going as deep as possible, and then you plop down a gazillion of those, and we'll see that in the next is it in chapter 5 where we see the graphics processor? Must be, because it's not here. Must be in chapter 5. So we'll see in detail what that looks like, from a, but it looks just like what we're talking about here. It's just that they plop down a gazillion of them. And the reason for that, by the way, is that here's in a game, here's what a game looks like. A game looks like X, Y, Z, and then this thing called scale, 0, 0, 0, down to X, Y, Z scale of a gazillion. a game, is made up of just a gazillion points. All the figures, all the buildings, all the people, each one, all of those things are just represented by a gazillion points. And every time, the thing has to rotate, every time you change your view, basically that requires you to multiply this matrix here by this matrix here and produce, another one of these matrices with all of these, every one of these points just transformed, slightly. And this is a 4x4. And this is a 4 by, I don't know, 4 by row by column, a gazillion by 4.
And
rows columns, yeah, gazillion by 4. I'm sorry, what?
modern GPUs are able to do that with actually millions of polygons at hundreds of frames per second. And I think
that's what
kind
these
of
are.
impressive.
That's what these are. These are polygons. So usually they do these with triangles, and each one of these points is one of the vertices of a triangle. And so all it's doing is it's moving every triangle vertice, like you said, at 30 frames a second. And to do that requires, just unbelievable, a number of floating point multiply adds per second. And that's how many are going on, an unbelievable number. It has to do this whole transformation for, every 60th or 30th of a second, or how fast it's doing it. Has to do, every point has to be transformed. And that's just a matrix multiply. And in this matrix multiply, by the way, is just the things you learned back in high school, sine and cosine of the angle that you want to move by. And that's all that matrix is made of. So it takes no time at all to compute that matrix. And then it takes, a long time to compute. Well, a long time. You'd think it would take a long time, but it takes very short time because they throw, it's an infinitely parallelizable problem. Every one of these transformations you're multiplying by the same matrix. And you could do them all at once if you had that much hardware. If you had a gazillion multiply adders, you could do every one of those transformations at the same time. Fortunately, they don't need that many.
Hi, Professor. The multiple for the matrix, I think you read it wrong. It shouldn't be 4x4. It should be 4 by gazillion. And then times gazillion by 4.
Well, I think I had them in the wrong order. Did I put them in the wrong order? Anyway, the inside, when you multiply matrices, the inside things have to match. So if you want to multiply 4 by 4, and the matrix, when we're done, looks like this, and it's row by column. So again, it's gazillion by 4. So that means that the 4 by 4 has to be on the other side, right?
You have to put it on the right.
Yeah, exactly. Right. Yeah, because these internal dimensions have to match, because you're multiplying this times this. So clearly that size there has to match that size there, and that produces that point there. And then this times this produces that point there, and so on. So, okay, anyway. Fallacies, pipelining is easy. Well, hopefully by the time we got through all this, that everybody in general believes that pipelining, the concept, the thought is easy, but it gets pretty detailed pretty quick. And to do it well, to make it continue to perform well, is you've got to do this data, these hazard detections, and you have to do the right thing as a result. And then he doesn't even mention the hardest thing, which is you have to do very good branch prediction, because if you don't, you're going to throw away most of what you do in the pipeline. If every 4 instructions you throw away 3 of them because you mispredicted, you can see you hardly make any forward progress at all. Now, of course, it's not that bad, but that would be the worst. In the worst case, you'd almost make no forward progress. I mean, so that's not going to work out. The branch prediction better be pretty good. So this is pretty obvious. Pipelining is independent of technology. Conceptually, what we're doing here, you could have always done. well, why haven't we always done it? Well, it's obvious because we didn't have enough transistors to do it. The very first computers, had to be dirt simple because again, the first ones were tube based, and if you put more than 1,000 tubes together, the likelihood of it staying up long enough to do a calculation was near zero. So, and then finally, we got to semiconductors where the reliability is reasonably high, but it still took us a long time to pack enough transistors to be able to do pipelining. Took several generations of processors before the first pipeline processors were built. The original 8080 and Z80 and 8086, none of those processors were pipelined. They just barely got them to work, period. So we know we need a good ISA design, but we know also that Intel got around that problem by just taking their ISA and transforming it into a good ISA in hardware. And again, they used Moore's law to give them that ability. They just had to wait one more generation of Moore's law and then do that transformation, and then they could build a back end that was just like MIPS and RISC-V and the rest of them. So all of these, this is Intel here, and here's a processor that you guys probably never even heard of. All of the microprocessors were built on this machine, the Digital Equipment Corporation VAX 11780. 11780 was the famous VAX computer that basically that the computer designers of the next generation used to put this company out of business. Basically, these guys built this computer, and then the engineers took and used that computer to design microprocessors, which then put these guys out of business. It's really quite sad, but that's the way the world works. Anyway, we got to get rid of all these complex addressing modes. Again, MIPS, ARM, RISC-V just have one addressing mode. That's all you get. And that makes it really, really simple, and you can make it really, really fast. And we didn't even talk about delayed branches. It's just like ancient history. Nobody talks about it anymore. So we have this circular loop here, although, it's not really, it's not circulating anymore, right? I mean, we basically fixed the ISA, right? Like I said, RISC-V, MIPS, ARM, all identical instruction sets, identical ISA, these three architectures. And so basically we're just now, making the implementations, as efficient as possible, and using Moore's law, what's left of it, to, do better branch predictors and do mainly what transistors are being used for today is to do, hardware accelerators. So people are building, specific things to do machine learning, just because you can do it more efficiently if you know that all you're going to do is an inference engine to recognize, voice, or to recognize, facial, things. If you design a special piece of hardware to do that, it'll be way more efficient, burn way less power than what you can do with a general purpose processor. So if you know exactly what you're going to do, people will build a so-called ASIC, an application specific IC, to do it. And we know that we get, that anytime we use parallelism, we can improve the performance. Pipelining is the simplest thing. And then, in general, SIMD and that sort of thing gives us, way more parallelism. And keep in mind, what we're trying to get is throughput. That's what we can really, improve, is the throughput. The latency, if you go from 5 pipeline stages to 14 pipeline stages, the latency actually goes up, but the number of instructions you can complete per second, goes down, or excuse me, goes up. The number per second goes up. At the same time, the latency goes up. So you're not improving the latency, you're just improving the throughput. And that's our goal. We don't really that much care about the latency, as long as the efficiency stays reasonably high. We have to fix all these hazards. We saw them all. We came, we saw, we conquered them all. And then finally, all this fancy stuff, which is not difficult to understand. Again, it's all just like that static unrolling. That's all we're doing. We're issuing multiple instructions at the same time. And we have to find ones that aren't dependent. And by loop unrolling, we can make ones that aren't dependent. And to the extent that we can't get rid of the dependencies, it limits how much ILP we can find. And this isn't so much a problem anymore. You know, the author earlier said, well, we couldn't bring the voltage down anymore, but we continue to bring the voltage down. So we can continue to throw transistors at the problem. It's just that the right way to throw transistors at the problem these days isn't by making the processors more complicated. It's by making the processors simpler and putting more of them down and letting software people have control of what all those processors are doing. That's the best way to build a efficient, fast processor, is put a whole bunch of them down there and let the software people figure out, how to use them all together effectively. And that's mostly the way the world is going these days. Mainly driven by the fact that in fact, some of the biggest markets out there are again, embarrassingly parallel the problems. Machine learning, training of neural networks is an embarrassingly parallel problem. Web search, servicing 3 billion people that all have their phones doing searches, an embarrassingly parallel problem. Problems that are easy to solve just by throwing more and more and more processors at the problem. Okay, remember, I'm sure you will, midterm next Tuesday. This coming Tuesday during class. It's about, I don't know. Some people, it depends on the person, how long it takes. Some people will get done in an hour. Some people will take, 2.5 hours. And it's, again, it's problem oriented, problem based. God, problem based. Not much else to say about it. So we have another quiz tonight, and the quiz again is for you'll see on the quiz again schematics like you're going to see on the midterm. That's not all of the midterm, of course, but for the chapter 4 portion of the midterm, it'll be questions similar to what you're going to see in these schematics. What is today? 28th. I got a Moderna shot today. I'm glad that I'm still upright. It should be open by now. Yeah, it definitely is open by now.
Hi, Professor. Do we have any coding programming in
Yes.
return?
Yes,
I
But
will
it's-
have to type or just select.
select. Do you know how, I did it for a couple of years where I had people write on paper programs. Do you know how hard it is to grade that? It's like, it's the biggest nightmare you could possibly imagine.
Okay, thank you.
You're welcome.